In this lesson, we're going to learn about parabolas and circles. So for the next few lessons, we will be exploring a class of equations called the conic sections. The graphs of these equations form the familiar shapes of circles, parabolas, ellipses, and hyperbola. We start by looking at each one individually, and then lastly we'll explore how they all relate as a group. The first conic section we explore is the circle, but for most of you this will be a review, so we'll not spend a lot of time on them. After that we'll look into the parabola in detail. Circles defined geometrically. A circle is the set of points in a plane that are equidistant from a central location. We give the coordinates hk as the location of the center of that circle, and define r to be the constant distance, which is known as the radius. And you may or may not have heard of a circle defined in that way, but if you see it visually, it really does make sense as to why it is the way it is. So I'll show you real quick the thought process behind it. So if I have a center point, which is C, and then R is my defining the radius between the circle itself that's going to be drawn and C, and then P is just some point on the circle. So if you notice, the distance between C and the point on the circle is 4 units. Now if I keep that distance constant and rotate point P around 360 degrees, we get the shape of the circle. So this is all the points that are the same distance away from point C. You know, if we change the radius or change where the center is located, this same result occurs. We just might have a larger circle or a smaller circle respectively, but the radius stays the same. That's what creates the shape of the circle. Now, developing a formula for a circle, we take the general situation, center point at hk, and xy as just some point on the circle. We know that we're keeping the distance between the center and that point xy constant. We're calling that the radius. So using the distance formula, we could say that r is equal to the square root of x minus h quantity squared. So we take the difference of the x1, x2, plus y minus k quantity squared. Or instead of expressing it this way, generally the standard equation for a circle is written as x minus h quantity squared plus y minus k quantity squared equals r squared. And there's the general form of a circle. Now, let's move on to parabolas. A parabola is defined as the set of points in a plane that are equidistant from a line and a focal point. So now we're not just looking at equidistant points from a single central value, we're looking at the constant distances between a point and a line. The line is called the directrix, and the point is called the focus. And just like with the circles, let's take a look at an applet to kind of help us understand, how this definition works and where the shape of the parabola comes from. So here I have a point that is a focus, and I have my directrix. So there's the point and the line. And what this definition says is the parabola is all the points P, so here's my point P, that are equidistant from the focus and the directrix. So if you'll notice, I have point C right here, and that's basically the minimum distance between P and the directrix. So the line that is at a right angle to the directrix is going to be the one that's the shortest distance. So the distance from P to the line is 5 units, and the distance from P to the focus is 5 units. Now that distance isn't going to be constant. If I move, if I move point C, which in effect is changing the location of P, the distances between the focus and point P and the directrix is changing, but it always stays the exact same value. So no matter where I stop on this parabola, I have that distance is constant. And if you'll notice, as I move that point, I end up with the shape that you may recognize as a parabola. Now, let's try some other values for the directrix and for the location of the focus. So let me tilt the directrix and let me move the focus closer to the directrix. And we'll erase what we have, and now I'll draw all the points that are equidistant. So now you might see that parabolic shape a little bit better. So it doesn't matter how it's tilted, you will always have the parabolic shape as long as you're finding the point that is equidistant between the focus and the directrix. Now, developing a formula for a parabola is a little bit more involved than developing one for a circle. But we're going to do it because I think it is instructive. So basically what I have here, I have the directrix, and I have my focal point right here. Now, those two objects, every single point on the parabola is going to be at equal distances between the focal point and the directrix. So what I need to do then is I'm going to define these two distances. I'll call this distance 1 and distance 2. And one thing we know about that is they are equal. We just showed in the construction applet that those two distances are equal. And we know how to calculate distances between points, but what we're going to need are locations of where these points are found. So the point on the parabola is easy. I can just call it xy. So all the points that exist on the parabola. But I'm going to need to be a little bit more specific for the points on the directrix and where the focus lie. Now, there is one location right here where the distance from the vertex, and this point right here is my vertex, from the vertex to the focus and from the vertex to the directrix, that's equal. And there's only one point where that occurs. So that's a special distance, and we call it P. And it turns out that P is an important number when it comes to creating our formula. So it's a good starting point. Now, I'm going to give coordinates to the focus based off of that. The vertex, I will say, is located at 0, 0. I can locate it at HK, but for our purposes, in order to derive this formula, it's going to be easier for us to assume the vertex is at 0, 0, and then use shifts and translations in order to move it later on. So that means the focus is at 0, P. Okay. Then the directrix is going to be the line not x equals, this is a horizontal line, so it's y equals negative P. And the next thing that I know is this point right here on the directrix. that point right there is a distance over x, and it's on the directrix, so its y value is still negative p. So that locates all my points that I need to work with. So d1 is the distance from the focus point to xy. So I'm going to write that as x minus 0 quantity squared plus y minus p quantity squared. So the focus is at 0p. That point on the parabola is xy. I'm just calculating the distance between those two. d2 is the distance from xy down to that point on the directrix. So it's going to be x minus x quantity squared plus y minus negative p quantity squared. And I have some things that I can work with and reduce. Let's see what happens. So in the next line, what I can do is first note that x minus 0 squared is just x squared. Y minus p quantity squared could be written as y squared minus 2yp plus p squared. And that's going to be equal to, well, x minus x is 0. Any 0 squared is just 0. Y minus negative p is just y plus p. So this is going to be y squared plus 2yp plus p squared. Now, I'm going to square both sides, because if I have the square root taken on both sides, I can square both sides and just kind of release what's underneath those square roots, which gives me x squared plus y squared minus 2yp plus p squared equals y squared plus 2yp plus p squared. And there's a bunch of terms on each side that are equal. So if I subtract p squared from both sides, they're going to cancel on each side. If I subtract y squared from both sides, they're going to cancel. Now, the 2yp's will not cancel because they're opposite in sign. So let's say I add 2yp to both sides. Then I end up with canceling it here, and I get x squared equals 4yp. Sorry, I wrote 2, but it's 4yp. Now, what I can do next is, in order to locate this instead at put the center at hk instead of at 0, 0. Then it works out that I can just use translations, and it's going to be x minus h quantity squared equals 4p times y minus k. That is the general form of a parabola. And in particular, this is a parabola that's going to open up or down. If you want it to open left or right, it would be y minus k quantity squared equals 4p times x minus h. And that's perfectly fine. You can have a parabola opening left or right. Now, this equation that I've just developed this is basically the same thing y equals a times x minus h quantity squared plus k, which is the vertex form of a parabola that you've seen in the past. So basically, if you subtract k from both sides, you get y minus k equals a times x minus h quantity squared. And if you divide both sides by a, 1 over a times y minus k equals x minus h quantity squared. So essentially it's the exact same thing where 4 times p is equal to 1 over a. So these constants that tell you like how wide the parabola is, there's just a different way of expressing them. Now, what's nice about the form we have it as is with the 4 times p is that the value p is used in locating the focus and the directrix, if you know where the vertex is, that is. So that's helpful. Another thing is you can tell how wide the parabola is by using this line right here. The line that is parallel to the directrix and passing through the focus. This is called the latus rectum. And I'll give you a moment to giggle, and when you're done, we'll come back to the mathematics. All right, you good? Okay, so it's called the latus rectum, and it is the distance between the 2 points that are, on each side of the focus parallel to the directrix. So what's nice about that is that distance is 4 times p, so this number exactly. So if you have that number handy and you know where the focus is, it's very easy to graph how wide your parabola is supposed to be. And that is very helpful to get a good, accurate picture. So the equation of a parabola in standard form will look like x minus h quantity squared equals 4p times y minus k if it opens up or down. Y minus k quantity squared equals 4p times x minus h if it opens left or right. So what I generally think about here is the variable that is not squared is telling you the direction of it. So the y variable is the y-axis, so up or down. The x variable is the horizontal, so left or right. So the variable that's not squared. As we said, it's very similar to the original vertex form of a parabola. But some things you want to remember. HK is always the location of the vertex. So if you have that point, that's a great place to start. P is the distance from the vertex to the focus and to the directrix. So if you have that number, that's very handy in graphing. 4 times p is the width of the parabola through the focus. If p is greater than 0, the parabola is either going to open up or right. Both of these are the positive directions. So if p is positive, it opens to the positive direction. If p is negative, the parabola opens in the negative direction. All right, let's work some examples. So find the vertex, focus, directrix, and axis for the following parabolic equation. Then provide a sketch and determine its domain and range. Okay, so the first thing that I look for is whether this parabola is opening up or down or left or right. So the variable that is not squared is the vertical variable. So it's going to go up or down. And I'm not saying which one it is just yet, but that's my first thing that I look for. All right, we're going to need the vertex. The vertex is relatively easy to develop. It's just the coordinates, in this case, -3, +1. The directrix and the focus, in order to come up with those, we're going to need to know the value of p. So from my formula, 4 times p is equal to -4. So p is equal to -1. So first off, what this means is my parabola is pointing in the negative direction, so it's going to be pointing downward because p is negative. And the distance from the vertex to the focus is 1 unit. And what I'm going to do is go ahead and plot some things. So the vertex is at -3, 1. So right there is my vertex. the parabola is opening downward, and p is equal to, let me say the absolute value of p is 1. So 1 unit above and 1 unit below is where we're going to find the directrix and the focus. So the directrix is going to be this horizontal line right here. And this is going to be my focus. Now, to determine, what's happening with the parabola, outside of those points, the length of the latus rectum is going to be 4 units. So 2 units on each side. All right. That shows me how wide this parabola is going to open up. And I can use that to get a pretty decent sketch of my parabola at this point. So I know how wide it is. I know that the direction that it's opening, where the focus and the directrix are, all of that stuff. I haven't labeled where these things are, but it's just fine to go ahead and start labeling those. See, the textbook often gives you a set of formulas for everything, but for me, all the different formulas make my head swim. What I do instead is I know basic facts of, how the vertex, the focus, the directrix all interact with each other. Then I use that with a drawing to try and help make sense of where they're located. And then I use the drawing to identify the coordinates of them. So the focus, if you'll notice, if you just find the location of the focus, it's at -3, 0. And that right there is a very easy way of determining where the focus is. Just use your picture. It's 1 unit away from the vertex, and in particular it's 1 unit in the y direction. The directrix, this is the equation of a horizontal line. The equation of a horizontal line is y equals the coordinate that it's passing through. So y equals 2. And the axis, that is the axis of symmetry. The axis of symmetry is a line that passes through the focus and the vertex and basically creates a mirror image of your parabola. So this is your axis, and it is a vertical line, so it's of the form x equals, and it's going to be -3. So x equals -3. Last thing that we need are domain and range. And I like to get domain and range just from the graphs. So the domain are all the points along the x where the function is defined, and the range is all the points along the y where the function is defined. So it's defined everywhere on the x. It's going from -infinity to +infinity on the x. As if I took this graph and I smashed it up against the x-axis, something would be defined at all points. The range is going from -infinity up to +1, and it stops there. It doesn't go any higher than +1. So that is the end point on my range. Next example, same thing we want to find here. Vertex, focus, directrix, and axis. Just a different formula, that's all. So this one, the variable that is not squared is the x. And that means that my parabola is going to open left or right. Now, the vertex is easily identified in this form. The x-coordinate here is -4. Just be careful because the x-coordinate of the vertex comes after the equal sign this time, but it goes with the x value. And +1. All right, now this time 4 times p is equal to 8, and if you solve that, then you get p is equal to 2. And that's the distance between the vertex, the focus, and the directrix. Now, it's a positive number, so that means I'm going to be opening in the positive direction. So this parabola is going to open to the right. Now I'm going to start putting some things on this graph. So the vertex is at -4, 1. And the value of p is 2. So 2 units in front of my vertex is the focus, and 2 units behind is the directrix. And my directrix this time is going to be going up and down. And the coordinates of this directrix, the equation of this directrix will be it's vertical, so it will be x equals -6. The focus, I could get the coordinates of the focus at this point. So the coordinates of the focus, if I just look on my graph, it's -2, +1. I could use a formula to get that, but again, I've got a picture, I might as well use it. Now the length of the lattice rectum is 8, so that means I'd go 4 units above and below the focus to find the next 2 points on my parabola. So it's going to be opening quite wide here. So a decent sketch is going to look like that. I haven't stated the directrix over here, even though I did put it on the chart. So I'll go ahead and put it over here. All right, the domain and range. And the only reason these will be in any way different from the last example is just because this is opening to the right. So in this case, the domain is restricted. So my vertex is, is at -4 on the x, and that's as far back as it goes on the x. So from -4 to +infinity. That's where my parabola is located on the x. And the y is -infinity to +infinity. On this next example, I want to find an equation of a parabola that has a focus at 3, 2 and a directrix of x equals -5. So instead of taking an equation and finding a graph, I want to take some properties and come up with an equation. But I went ahead and put a graph here because a lot of times I find it useful to organize the information on a graph in order to determine where everything's supposed to be on the equation. So let's see what happens. So the focus is at 3, 2. So I'll go ahead and plot that right there. The directrix is x equals -5. So the directrix is back here. Now, the things that I know first off is because of the orientation of the directrix and the focus, this parabola is going to be opening to the right, which means 2 things. First off, the value of p is going to be greater than 0 whenever I find it. And secondly, the form of the equation that I'm going to use will have the x variable as my non-squared variable because it's a horizontal, and that x is the horizontal variable. So that gives me a lot of places to begin here. I don't know what p is, and I don't know what h and k are, but I think I can find all those out pretty easily because I know that the vertex is the center point between the directrix and the focus. So the focus is here at 3, 2, and so that is 3 on the x. So, and the directrix is -5 on the x. So if you take 3 minus -5, that's 8. So 8 units away. Halfway is 4 units. So that means my vertex needs to be right there. So that's 4 units to the directrix and 4 units to the focus. It's halfway in between. So that tells me, first off, p is equal to 4, but then also I can calculate the coordinates of the vertex. In this case, they're going to be at -1, 2. So my vertex is at -1, 2. Those 3 pieces, that's all I need in order to create the equation of the parabola, which in this case will be y minus 2 quantity squared equals 16 times x plus 1. And there's an equation of a parabola with those specifics. Find an equation of a parabola that has a vertex located at 3, -4 and a focus located at 5, -4. So 3, -4. So 3 on the x, -4 on the y should be approximately right here. 5, -4 is going to be right here. And let's label what these are. This is a vertex and this is a focus. Now there's a lot of things I can derive from this. So first off, because that's how my vertex and focus are oriented, I know that my parabola opens left and right. One of the two. And I know that p is greater than 0 because the focus is in front of the vertex. I know the value of p because I can find the distance here. It's only 2. And knowing that, along with the location of the vertex, which I was just given as 3, -4, I can take the general equation here, y minus k quantity squared equals 4p times x minus h. So that's a parabola that's opening left and right. And just plug in my values for p, h, and k. So y plus 4 quantity squared equals 8 times the quantity x minus 3. Find an equation of a parabola that has a vertex located at 4, 3 and a directrix whose equation is y equals 6. So 4, 3 is the vertex and the directrix is y equals 6. So y equals 6 is going to be right here. Now, knowing that, I can figure out all the pertinent things that I need here. First, I know that this thing is going to be opening downward because it's going to open the opposite direction of my directrix. You know, I don't have the location of the focus or the lattice rectum or anything. I don't know how wide it's going to be, but I know it's going to open downward. So because it's opening downward, that means the equation of this parabola is going to be of the form x minus h squared equals 4p times y minus k. And I already know what h and k are. Those were given as the vertex. So I just need to find p, which is the distance between the directrix and the vertex. And that distance, you could just basically count it, you know. So starting from 3 on the y, so 4, 5, 6, so that's 3 units. So this will be x minus 4 quantity squared equals 12 times y minus 3. Find an equation of a parabola that has a vertex located at -3, 0, and the length of the latus rectum is 6. You may assume the parabola opens upward. Okay, so in this example, we need to just start taking the different pieces that we have and get them situated in such a way that we can work toward an equation. All right, so first off, the vertex is located at -3, 0. So if I sketch this, here's -3, 0, right there on the x-axis, and that's my vertex. Length of the latus rectum is 6. If I knew where the focus was, that would be a very helpful piece of information, because the latus rectum passes through the focus, but I don't know where that is right now. But the other thing that I'm told is that the parabola opens upward. So this parabola, I'm just going to put dashes in just because I'm not sure exactly this is to scale. I'm just kind of fitting things together here. If it opens upward, that's actually a really helpful clue. Because that tells us that our equation has to look like x minus h quantity squared equals 4 times p times y minus k. So because it's opening upward, that tells us which of the two variables has to be squared. So that's a big help. Also, since we already know the vertex is located at hk. So the coordinates of the vertex is always at hk. So I know that h is -3, k is 0, so that gives me x, so it's minus h, so minus -3, so x plus 3 squared equals 4 times p times, well, actually it's going to be y minus 0, so let me just put a y in there. Okay, now we have to handle this 4 times p. Alright, so again, I don't know where the focus is, although we probably have enough information that we could find out where it is. But wherever it is, the latus rectum is a line that passes through the focus, and that's this line that I've drawn, and I'm hypothetically drawing it here. So this would be my latus rectum. I know that the length of this line is 6. Now, the other thing that we talked about at the earlier part of the video when we were describing parabolas is that the length of the latus rectum is equal to 4 times p. So that's the last piece of this equation that we need, is 4 times p. That's just the value 6 here. So we can actually just directly substitute and write this is x plus 3 quantity squared equals 6 times y. And now all the different pieces of our equation are fit in. So this is the final answer.